When I say the event of observing less than 4, so my favorable outcome should be 1, 2, 3. So if I say the event is less than or equal to 4, then 4 must be considered there. So again, we have n of E2 is equal to 3. Therefore, P of E2 is also 3 by 6, which is 0.5. Now, since the probabilities for the event E1, E2 are same as 0.5, you can call E1 and E2 as equally likely events or equiprobable events. So whenever you observe two or more events with same probabilities, the events are also said to be equally likely, and each of these outcomes are also equally likely. So you can take what is the probability of observing 1? It is 1 out of 6. Probability of observing 2, 1 out of 6. So one possibility out of 6. So each of every outcome has the probability 1 by 6. They are also called as equally likely. Now, observing the event of interest as getting an even number. So again, there are three cases, 2, 4, 6. Therefore, probability comes to be 3 by 6. And multiple of 3, only 2 favorable outcomes, 3 ones and 3 twos are. So we have 3 and 6. So n of E4 is equal to 2. Therefore, probability of E4 is equal to 2 by 6 or 0.33, 33% chance of observing a multiple of 3. So this could be one of the problems in the examination, and the most likely question, as said, will be on tossing 2 coins or 3 coins and then throw off 2 dice together. So again, if you remember the concept A power B, number of elements in a sample space, when you repeat an experiment which has the basic possible outcomes as A and B times you are repeating the experiment, then the total possibilities in the sample space will be A power A. So if I throw a dice once, I'll get 6 outcomes. So this is our A. If I repeat it twice, then I'll have A power B, which is equal to 6 power 2, which is 36 outcomes, 36 possibilities. Naturally, so dice 1 has 1, 2, 3, 4, 5, 6 as the outcomes. So the second dice will have 1, 2, 3, 4, 5, 6 matched with each of these outcome of 1. So 6 cases into each of 6 of the case dice 1 will get you 36 possibilities, and we can use the same notations like h comma h to indicate the dice. So 1 1 1 2. So this could be often misleading as 11 and 12. So just to be mathematically correct about the numbers, we enclose them within the common braces with commas. So 1 comma 1 indicates the outcome when you toss 2 dice, where 1, the very first number indicates the outcome of dice 1, second one indicates the outcome of dice 2. So if you look into the possibilities, you will have a set 36 outcomes: 1 1 1 2 1 3 1 4 1 5 1 6, and then you could have 2 1 2 2 2 3 2 4 2 5 2 6. So if you see that whenever you conduct the experiment, only one of these elements, whatever we have written, happens. Therefore, they are all mutually exclusive. And if you look into the probability of happening, only one could happen out of the 36 cases. So each of these outcomes has probability of 1 by 36. So which make all the events equally likely. Coming to the events, now you could talk about getting odd number in the first case and even number in the second case, or sum as a multiple of 2, sum exceeding a certain quantity, sum or product below a certain quantity, So all such possible cases could be asked as the event. So the method of finding probability is again same. Study the event, observe the event properly, pick the elements from the sample space and create the favorable set for that event, and then count how many elements are there in that event and obtain the probabilities. So this is the sample space, and let me take one or two events. So if I want to observe the case where both are multiple of, let me say 2, and then sum is multiple of 3, and let me take a product less than 12. So these are some of the events of interest. So I am interested in observing what is the chance of getting the outcomes, both the outcomes as multiple of 2. So I'm basically talking about my dice 1 should also give me an even number. Dice 2 must also give me an even number. So if you look into the favorable cases, so I have 2, 2, 2, 4, 2, 6, 4, 2, 4, 4, 4, 6, and then 6, 2, 6, 4, 6, 6. So these are the 9 cases out of 36 which are producing both even. If you look into the remaining cases, in there one is observed to be odd, though I have an even here 2, 4, 6. The other number is an odd number. I cannot consider because my expectation is both to be even. So you have to write the set clearly in the examination. Don't just write n of e. So E1 is equal to 2, 2, 2, 4, 2, 6, 4, 2, 4, 4, 4, 6, 6, 2, 6, 4, 6, 6, and then write the count and then compute the probability. So we are observing 9 outcomes which are favorable to this. Therefore, the probability will be 9 over 36, which comes to 0.25. So there is 25% chance of observing both even numbers when you throw 2 dice. Similarly, when I am interested in, say, the sum is a multiple of 3. That is, you will throw 2 dice, you will add both the outcomes and you see where the sum is producing a multiple of 3. That is, when you add, the total should be like 3, 6, 9, 12, 15, and so on. So here, when I look at the sum, it is just 2, 1 plus 2. So I have the sum to be 3 here, then 4, 5. So here the sum comes to be 6. Then 2 plus 1 is 3, 2 plus 4 is 6. Then I will have 8, 4, 5, 6, 7, 8, 9. Then 5, 6, 7, 8, 9. 6, 7, 8, 9, 10, 11. Then I'll have 7, 8, 9, 10, 11, 12. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So out of 36, there are 12 cases where my sum is equal to 12. So the chances or the probability is 12 by 36, which is 1 over 3 or 0.33. So 33% chance that you will observe the sum to be a multiple of 3. So lay down certain events of your interest where the product is multiple of 3, sum less than 7, sum greater than 7. So this less than 7, greater than 7 is the most event observed in any of the gambling situation where you toss through dice. So if you have visited the farewells or any of such simple occasions, so you could observe an experiment or a game where 2 dice will be rolled. You will bet on whether you observe a sum less than 7, equal to 7, or greater than 7. So compute the probabilities and see where the chance is more, so that you bet on that particular event to, uh, you could say, maximize the outcome or the payment. So this is about the simple definition of probability where we are using the sample space. Oh. So as said, these are usually with respect to the assumption of equally likely as well as disjoint or mutually exclusive. But when we look into the practical situations of, say, observing this, that might not be a same situation based on the theoretical assumption. Say, as said, the gender of the person you are about to, I mean, the patient which you are about to visit, so could be male and female. But in the past few days, you have observed that the clinic is only filled with, say, female patients, then you might suspect easily that the next patient about to visit will be a female. So that could happen. So this is because of whatever the observation you have made. So when I say you're making some observation, you are collecting the data. So collection of data by conducting some experiments will lead you to a decision making, though there is some uncertainty. So this technique of finding probability based on the observations actually made, that is called as statistical method, and this is the most widely used method of finding the probabilities. So if you say what is the chance that tomorrow there will be rain, they have observed in previous cases how many times it has rained on June 25th. So they'll compute the probabilities based on the data. So what is the probability that a plane which has, taken its flight will land safely? So that in these cases, say it is hard to come up with a sample space. What could you say about sample space? What is the chance that the flight taken will land safely? There is no sample space. So you could answer that question only based on the supportive data. So how can you use this supportive data in answering that question? So you will see that particular plane, say plane named with XYZ, how many times it has taken. So in the various certain cases should be there. So I say the plane usually travels from A to B. So whenever it is traveling from A to B, how many times it has landed without any difficulty. So I'll call that as landing successfully. So that we will observe, and I'll call that as N. So in the previous cases, let me say that the flight has taken around, say, 1,000 such flights from A to B. Now, question, how many times it has taken flight? So this is our answer, which is N is equal to 1,000. So it has taken 1,000 flights. Now the question, out of these 1,000 cases, how many times it landed successfully? So when I say landed successfully, without observing any technical problem, without observing any problem with the passengers or the crew. So there could be cases where, there will be some minute technical problems or the problems with the crew, problems with the passenger. Those are, which the data may be unavailable to a layman, but the data will be available in the, crew. So they could give you an answer. So at certain number of times there was, trouble with the engine, some switches were not working, but yet we have, landed the flight successfully. So let me say around 980 times this has happened. Then I could obtain a proportion for that case as, so we have obtained the counts. Now the count will be converted into proportion, and if you're computing this proportion of, let me say, successful landing, proportion of successful landing of flight XYZ when it travels from A to B is 980 by 1000. So I could say there is 98% chance that your flight XYZ will land safely. 98% chance that your flight will land safely. So this is how your past data helps in predicting the chances. And of course, as time changes, there will be much newer data added to this. Suppose I say after 1 month, if I check back what is happening, so in another month, maybe the flight has taken 50 more flights, and maybe of those 30 cases, it has landed safely. So now the new count is this and this, and in that case, the probability is 1050 over 1110 to some number. So that becomes the probability. So every time when I approach this method, as and when I get some new data points, the probabilities will be revised. So based on this particular technique, now you can come up with the experiments where you cannot talk about the sample space, you cannot talk about the outcomes which are equally likely. In that case, statisticians say conduct the experiment for a large number of times, observe the data, from the data generate the proportion for that particular event. You can take that proportion as probability only under the case where you are conducting the experiment for a large cases. Because for few cases, only by chance you could observe that. But for a large cases, all possibilities will be included. So the proportions gives you very much good estimates for the probabilities. So summarizing this in the mathematical form, so if I say if you are conducting the experiment for n times, out of which you have observed the success or the favorable outcome for n times, where your n is very large, in that case we call probability of event as that limiting ratio m by n. So this just indicates that n should be large. What is n here? N is the total trials of the experiment. N is the total trials of the experiment, and m is the number of times out of n your favorable outcome or favorable event has happened. So understanding this by a simple example, let me take the same experiment of throw of a dice. So in the previous case, I said I have my sample space S is equal to 1, 2, 3, 4, 5, 6. And I said, if you want to observe what is the outcome when you want to expect the outcome to be 1. So your event is getting 1 as the outcome, getting number 1. So it has only one case, therefore it is 1 by 6. So if you observe what is the probability of getting 2, so again we say your event has only 2. So here I'm interested in observing this number. So your E2 has only that number in the set. So your n of E2 is also 1, therefore probability is 1 by 6. So if I am using the classical definition, so if I say my x is the outcome, I say my x is the outcome of dice. So these are the 6 possible cases. And let me say what is the probability of that each of x. Classical definition assigns probabilities as 1 by 6. But often this is not true, because whenever in our childhood or whenever we are leisure, we try to play the game of dice or your snake and ladder. So at certain times you are bound to win. Your particular coin is here. Now if you want to win the game, you are expecting the outcome on the dice to be 1 so that you can reach that winning scenario. But you will take a number of trials. You will throw the try for 10 times, 12 times, but yet you have not observed the number 1. So your die is such that it is avoiding the concept of equally likely. Equally likely and here, if you throw the die 6 times, 1 times all the numbers should be observed in those 6 throws, but that never happens in a practical situation. So that's why most of the cases the gamblers or the people who are in a competitive situation, they don't solely believe on this. They look into the data observed. So how they apply this definition? So I said, now what you have to do, you have to come up with a probability. What is the chance that when I throw this particular die, I'll observe one. So to come up with an answer for that, which is the most appropriate way, so we suggest you throw that particular die, throw that particular dice, say 1,000 times, because the experiment must be conducted for a large cases. Only then you get a number, a proportion which is very much close to the probability. So throw the dice 100 times, and each of the 100 times count how many times you have observed that particular outcome. So you're throwing the dice 1,000 times. Now out of the 1,000 times, obtain the count, how many times you are observing 1, 2, 3, and so on. So basically, the number of repetitions of 1 is nothing but the frequency. So you can come up with the frequency distribution. So I have observed 1 200 times, maybe 2 150 times, 3 only 50 times, 400 times, 4. So you get certain count. Now convert this count into the proportion. And one such proportion, what we have learned is relative frequency. So when you divide each of the frequency by the total n, we get relative frequency. Now whenever you have n large, you can take this relative frequency as probability. And this works very well with the most of the practical cases. So probability of observing 1 is 2 by 10 or 200 by 1000, which is 0.2. So the chance of observing 1 is actually 20% for this particular die. It is not 16% or 1 by 6. So this method helps you in computing the probabilities. Now if you are into a survey, what is the chance that if I visit this particular locality, I'll get maximum females? What is the chance that I'll get maximum males? In that case, count how many males and females are there, or use the sex or the gender ratio of that particular city or the locality in coming with the values of the probabilities. So from this example, what we are observing is that if you have a frequency distribution and if your total frequency is very large, you can obtain the ratio f by n, which we call as relative frequency, and those things can be taken as probability. And this is actually the definition of relative frequency whenever your total frequency is large. Therefore, this statistical method is also called as relative frequency approach or empirical method of computing the probabilities. So for this, you have to actually have either the past data, or if you are freshly computing the probabilities, then you have to conduct the experiments repeatedly under the same conditions for a large number of times in order to get the count, so that the proportions can be easily obtained. Okay, so this is sufficient knowledge, I guess. So we have just understood the basic definition, some of the terms involved in the computation of probabilities. I can get these things in unit 14 or chapter 14 of your block 4, or if you are visiting that first PUC book, it is in chapter 6, 7, 8, 9. Chapter 9 of that book. So there are many such numerical problems. So don't look into the complex problems. Just as said, look into the problems related to coins, dice, then lottery tickets, or if you are, selecting some students in order to build up a cricket team, or in order to come up with a quiz team. So such cases are simple problems are sufficient to understand the knowledge and the computational methods of probabilities. So next concept when we have learned the probability is what called as random variable and probability distribution. So this is an important topic. So once you know the distribution of a random variable, and if I say that probability distribution is actually a normal distribution, then the hypothesis testing and the confidence interval estimation or the much of the parametric inference becomes very easy. So the first concept now after understanding probability is probability distribution of a random variable. And from the beginning of the sessions, we have understood the word what called as variable. So you are collecting the data on what called as quantitative characteristic, which varies from time to time and place to place. And we called this quantitative characteristic as variable. Now, what we do is we try to convert the elements of sample space into numbers, into real numbers, and whatever the real numbers you observe, those are called as the random variable. So basically you have to come up with a definition which we mathematically call as function. So function such that it converts s into your variable which is x. And if you could list out all such possible x along with their probabilities, that is called as probability distribution of a random variable. That is similar way to that of a frequency distribution. We define frequency distribution as set of all possible values taken by the variable along with the frequencies. Now here the variable is a special variable which is called as random variable. We'll say why it is called as, we'll see why we'll call this as random variable. Now, what if you write that values taken by the random variable along with the probabilities, then such a distribution is called as probability distribution. So you have x, you have the probabilities of x. And if you look into the total probability, in certain case, that will be always equal to 1 because total of relative frequency is always equal to 1. Therefore, total probability is equal to 1. Now you can ask me how this x works when you don't have the sample space. So I gave you an example about cases where the sample space is difficult to construct, but think of any random experiment, whether you talk about the uh, landing of a flight or giving birth to a baby, observing defectives at the production, all those things will have the hidden technique of sample space. That sample space could be discrete, it could be continuous, it could be finite, it could be infinite, but for us, only the outcomes and counts will be visible, but the sample space will be hidden. And we have already observed that the exact elements of the sample space is not required. Only we need the count. So we need not worry about the sample space. But if you are using the concept of classical approach, sample space must be observed. Now let us understand how to create this x from the sample space. So let me take the good old example of observing the outcomes when I toss 2 coins. So this is my sample space. Now I have to define a function, define some function, which I say the mathematical way, such that this yes will be easily converted into real numbers, say x. Okay, so there are many possible ways of defining that. So I could say, let me say x is the function such that I'm counting number of heads. So what I do here, I'll toss 2 coins and I'll observe or I'll count how many heads in total are possible. So when I toss 2 coins, so this is the sample space. So if HH happens, then I say 2 heads are observed. If HTS happened, then I say 1 head is observed. If TH happens, then I say 1 head is observed. If TT happens, then I say no heads or 0 heads are observed. So this definition, number of heads, converts each of the sample space into real number 0, 1, 2. And if you look into the total possibilities, so my x can take 0, x can take 1, or x can take 2. So x can take this 1 as possibility for these 2 cases. So this is called as an onto mapping. So each of this could have same x value, but no 2 different x values will have same element of the sample space. And then if you are assigning x is equal to 2, that cannot be, mapped with HH, and I cannot have a case where what I'm telling here. So that could be, I say the inverse should be just on a mapping of 1. So you can have multiple events mapped to 1, but you cannot have multiple elements of x mapped to the same item. So same item here cannot be mapped into two numbers. Only in that case we call it as a random variable. So in this experiment, my random variable is number of heads observed when I toss two coins. Now similarly, if you extend the experiment of tossing three coins, then you have n of s is equal to 8 possibilities. So when I toss three coins, so simply you could say more coin toss ಮಾಡಿದಾಗ you could observe all tails, you could observe none of the tails, you could observe one tail or two tails, and there if you define x as number of tails instead of counting number of heads. So in that case, again x takes the possible values 0, 1, 2, 3. So your 0 will happen with the case of sample space HHH. One tail can happen in this way. Two tails can happen in this way. And three tails can happen in this way. So which makes all the 8 possibilities. Now think about possibility for a particular case of x. So this is your x. So this is your event. So you can come up with a probability. So totally it is 8 because we are talking about 3 coins. So this will be 1 by 8. There are 3 favorable cases, 3 by 8, and one favorable case for the last. It is 1 by 8. If you look into the total probability, 1 plus 3 plus 3 plus 1, which is 8 by 8, is equal to 1. And such a distribution where your x is discrete, and for each and every possible cases, you can assign the probability. That distribution, probability distribution, is given a special name called as probability mass function, abbreviated as PMF. So PMF indicates the probability distribution of a discrete variable. Now, as said, your sample space could be continuous. So whenever you talk about continuous sample space, you could talk about continuous random variable. Say you are counting the time spent in queue at a bank. So you could spend 0 minutes, you could spend 0.5 minutes, you could spend 30 minutes, you could spend 60 minutes, you could spend 25 minutes. So when I look into the particular case, so it totally becomes a continuous concept. So writing each and every possibilities may be difficult. So you could say I could spend 0 to 10 minutes or 10 to 20 minutes and so on. So again, if you look into the case, we are talking about the concept of continuous frequency distribution. So you are visiting the bank, say, many times. So you have made past 100 visits to the bank. Now you create your frequency distribution out of these 100 visits, on how many visits you were there for in between 0 to 10 minutes, maybe 30 cases, 10 cases of your 100 visits, you spent 10 to 20 minutes. So you could come up with a distribution and you could obtain the relative frequencies or the probabilities. Then such a distribution is called as continuous probability distribution. And again, if you look into the case, you will have the total probability to be equal to 1. And such distributions are called as probability density function. The reason, again, it is similar to the graphical approach. So when you have discrete points, you can actually erect rectangles. Now, since it is discrete cases, the width of the rectangle will be just 1. So it is basically straight line, and your height is such that it is your probability. So if you have a discrete probability distribution, you can create what called as probability histogram by taking your x values on the x-axis, probability values on the y-axis, and each of this indicates the mass of the probability. That's why it is called as probability mass function. But when you look into the continuous case, it actually produces a mathematical function. So have 0 to 10, probability is say 0.3, then 10 to 20, it is 0.1, then 20 to 30, it is 0.2, then 30 to 40, it is 0.4. To have the scale. So it is producing a continuous form. And if you're talking about a more very general situation, then you could end up getting the probability curves in the form of your frequency curve. But here we are not using frequencies, but we are using the probabilities. So they are called as probability curves. And if you look into that, you can talk about the density, you can talk about the area under the curve. Therefore, such continuous distributions are called as probability density functions. So I'll stop here. So please go through the chapters. I said chapter 14 in your book and chapter 9 and 10 of the first PUC. So most of the things what I have covered comes under this. So in the coming classes, I'll talk about some standard probability distributions. Now the cases and examples what I have discussed today, they come under the category of observed frequency distribution or observed probability distribution. So when I say observed, we mean we are conducting the experiment, we are observing the data. From the data, we are producing the distributions. Now, whenever I repeat the same experiment in the coming days or in the coming time, they have a tendency that the different frequencies, different probabilities could be observed. But if I look into the cases where certain variables, certain random variables are bound to certain assumptions or theoretical concepts, then such probability distributions are called as standard probability distributions because they are not based on the practical approach. That is, you are not conducting any experiment, you are not doing any practical analysis there. You are using the concepts of theories, the results, the theorems, certain mathematical laws, and based on that, you will come up with the probability. So probabilities will be obtained using these concepts. Then such distributions are called as theoretical distributions or standard distributions. Now, any such distribution as observed could be a discrete distribution. It could be a continuous distribution. So I'll wind up the session here. So if you have any doubts, you can ask. Unmute option ಇದೆ ಅಲ್ವಾ join ಆಗಿ ಮತ್ತೆ less than 1 minute ಇದೆ. If you have questions, you can join back. Otherwise, no need to join back.